Good afternoon, I'm Saritha Kumari, Assistant Professor in EEE Department working at the Institute of Aeronautical Engineering College, Dundigal, Hyderabad. Today I'm going to give the lecture on topic Inductance of Composite Conductor. So it is mapped to CO1, CO1 only. So just a revision of the previous topic. So the previous class lecture, this is what I explained: the inductance of a single phase transmission line when there are two conductors are there. And each conductor is stranded conductor. Okay, first for a single one conductor, for only one conductor. So we know that this is the first one is the total flux linkages. So that is given by 2 into 10 power minus 7. So that means it has the total internal flux and external flux. So finally the sum of those we have seen 2 into 10 power minus 7 I log base E log capital D by R dash. So that is a total flux linkages expression. From that the inductance L is given by, from the definition of inductance, flux linkages to the current. So psi by I, so which is given as 2 into 10 power minus 7 log base E capital D by R dash. So units are henries. So the same expression written in the next line in terms of log base 10. So that is 0.4605 log base 10 capital D by R dash. So that is given for millihenries per kilometer. Okay, just remembering the first this one is sufficient. Okay, anyway, this is the inductance expression for one conductor, single conductor. But we know that a single phase transmission line having two conductors. Okay, so that means one there is a two conductors. One conductor, one is phase, the other one is a neutral. So one acts as a go conductor, the other one acts as a return conductor. So anyway, there are two conductors. So if we write with respect to one conductor, the inductance is L1, which is nothing but 2 into 10 power minus 7 log base E capital D by R1 dash. And with respect to the another conductor, second conductor, the inductance is L2, so which is 2 into 10 power minus 7 log base E capital D by R2 dash. Now finally the total inductance, that means for the transmission line, for a single phase transmission line, the total inductance is given by sum of the two, L1 and L2. So L is given by L1 plus L2, which is given as 4 into 10 power minus 7 log base E capital D by because log A plus log B means log AB. So D by capital D by capital. So we get exactly log of D square by R1 dash R2 dash. So if we get this, if we take the under root in numerator and denominator, so this 2 will goes off, and the in the denominator we'll get the root. So this is a total inductance L expression. Now we know that both conductors in a single phase transmission line usually have the same radius. So let us say that R dash, both are R1 dash and R2 dash are equal to R dash. Then R, which is nothing but R dash, let us take. So then the expression for L is given by final expression 4 into 10 power minus 7 log base E capital D by. So this 2 becomes R1 R dash square. So then root and square gets cancelled. Finally, this is the expression for single phase transmission line. So for a single phase transmission line, the inductance expression where there are two conductors, you can see on the right side, one is a conductor A, another conductor B, okay, and both are standard conductors, okay, this is a standard conductor. So how it looks like, so the total inductance expression is given by 4 into 10 power minus 7 log base E capital D by R dash Henry's per meter length. So that is the single phase transmission line inductance expression. Now also consider, um, suppose there are group of conductors are there, which are group of conductors which are side by side. Then consider, you can see in the figure, um, here a group of n parallel conductors, you can see 1 2 3 and so on, and 1 2 3, then j conductor also there in between, okay, I conductor, j conductors are there, okay, and so on. And then suppose we want to write the flux linkages of one conductor in that group of conductors, okay. So then the flux linkages expression is given by, okay, let us say we are writing the flux linkages of ith conductors, okay, ith conductor delta uh, delta I. So that is given by 2 into 10 power minus 7, because each conductor having its own current. Here I have first conductor having its current I1, let us say second conductor 2 having its own current I2, and so on, like that. Based on that, the flux linkages of ith conductor is written as expression 2 into 10 power minus 7 into I1 into log of 1 by d I1, okay. So that is for first conductor, due to first conductor. Then second conductor, due to second conductor I2 log of 1 by d I2, excuse me, plus log of 1 by dii. So that means due to its own flux, ith conductor own flux. Then and so on, due to last conductor, nth conductor. We have total n number of conductors. So then in into log of 1 by din. So units of flux linkages, Weber turn per meter. So this is just to know that flux linkages of one conductor when there is a group of conductors. When there is a group of conductors like this. Okay. So now um, now we'll see the inductance of a composite conductor. We'll see inductance of a composite conductor. Composite conductor means a standard conductor. Okay. So what is the inductance? How to calculate the inductance? Previously we have seen for a single conductor. Okay. So if it is a standard conductor, okay, this previously we have seen for a single conductor. If there is a single conductor, the expression we have seen the derivation. Now for a standard conductor, what is the expression? Okay, expression of inductance. Now consider, here they have considered two group of conductors. Okay, so that means two conductors, each one is a standard conductor, conductor A and conductor B. Conductor A having n number of conductors, and say conductor B has total m number of conductors, right? So and the first conductor A starts with 1 2 and so on I, finally n, and B conductor B starts with 1 dash, conductor 1 dash, okay, uh, like that. So 1 dash, 2 dash and so on, j dash, finally m. So just know that, okay, conductor A has total number of conductors n. B has m number. Okay, now um, this is a now we want to first we write the inductance. First we write the flux linkages. Okay, then only finally at last we come to the inductance, right? So now look at the first point. The figure shows here single phase line. Okay, consisting of composite conductors A and B having A having n parallel filaments and B having n parallel elements. Okay. Now, let us assume current is equally distributed among the filaments of each composite conductor. Okay. So, current is equally divided. If we say current in conductor A is I, the total I is equally divided among total n number of strands and number of filaments. So that's what the next point is talking about. So then each filament of conductor A is carrying a current of I by N. So if total current is I, if there are n number of conductor strands, then what is the current in each strand? I by N. Then similarly in conductor B, current is minus I, right? In a single phase line, one conductor is acts as a go conductor, another conductor acts as a return conductor, return path. So if one conductor current is I, then automatically the other conductor current is minus I. That's why the current conductor B, each filament carries current of minus I by M, because total conductors are total conductors are M. Now, the flux linkages of ith filament in conductor A. Okay, so ith filament, so conductor A, we have, there is a, okay, which starts from 1, 2, okay, one conductor, two, then and so on I, then finally N, right? Now, here, sorry, we are writing flux linkages of the ith element in conductor A. So, previously I have given the expression in a group of conductors, the flux linkages of one conductor. So, based on that knowledge, so for ith filament here, it is written as flux linkages. Uh, Sigma I is equal to R lambda I. So, um, just I say that uh, psi by I. So, flux linkages, I read it as psi. So, psi I is equal to, so we know that it consisting of currents in each element, each conductor, each filament. Okay. So, correspondingly, first, it is with respect given for conductor A, all conductor A filaments. Okay, so this is what it is. So 2 into 10 power minus 7, each conductor in conductor A, each filament here carries a current of I by N. So that's why it is taken common. So now, first due to first one conductor 1 in conductor A, that is log of 1 by d I1, right? Next, due to conductor 2, it is log of 1 by d I2, and so on, log of 1 by d II plus, and so on. Last element is n, right? So log of 1 by d In. So this is with respect to filaments of conductor A. Then, because we know that there is conductor B also there, just beside, so there is a, we have to consider the flux linkages due to that also. So that's why the current in the conductor B is minus I by M, we know. That's why it continuation of the expression minus 2 into 10 power minus 7, current in each filament of the conductor B is I by M. So into log of first in brackets, first one is conductor 1 dash. So filament 1 dash. So log of 1 by d I 1 dash. Next log of 1 by d I 2 dash, and so on. Okay, log of last element here is m. So log of 1 by d I m. Now finally we rearrange this total, because we know that log a minus log b, log a minus log b is what? Log a by b. So log a by b. So the finally the expression next step is 20 to the power minus 7 I is common. So here this whole is what? This whole is first one. This part is 2 into 10 power minus 7 I. Okay, I can write log of d I1, all are sum, right? So log a plus log b means log a b we can write. So log of d I1 log d I2 and so on, log of d in. Okay, whole power what? 1 by n. This is whole power 1 by n. Okay, divided by so this becomes all are 1 by, right? Okay, divided by log of 1 by the down one, d I1 dash d I2 dash d im. Okay, whole power 1 by m. So now this whole one, what it will become, we can write the next term like this, right? From this, whatever we can see on the slide, 2 into 10 power minus 7 into I log of, so this down one comes up, so it is written as, okay, d I1 dash d I2 dash and so on d im whole power 1 by m by d1 d I1 plus di1 di2 so on dii and so on din 1 by n. Okay, now this is the flux linkages for ith element. Now now uh, the inductance, then the inductance of this ith element is given by, we know that, so because it carries a current of I by n, so psi I by n. So what it will become, so automatically I gets cancelled and the above expression, this 1 by n comes to numerator, 2n into 10 power minus 7 log of so this log term is remains as it is. So now this is the inductance for ith element. Now now the average inductance, because this is a group of conductors, so the average inductance is considered. So the average inductance of any one of the strand or filament in a group of conductor A. So that is L average, okay, which is given by L1 plus L2 plus, okay, and so on, Li plus Ln, okay. So in between Li also there. Overall, okay, divided by n. So that is our average inductance. Now, finally, the inductance. The inductance expression, okay, the conductor A inductance expression is given as, okay, obtained as like this. Okay, so since conductor A is composed of n filaments which are electrically connected in parallel, so it is given by LA is equal to L average by n, because n number of filaments are connected electrically in parallel. So finally the inductance of the conductor A is given by this average inductance by average inductance by N. Okay. Now, which is nothing but L1 plus L2 plus, we know what is L average. So L1, which is L1 plus L2 plus, and so on, Ln by N, again one more N, so N square. So now substituted. Now substituted for L1, L2, okay, and Ln. So finally, so this is what we have, okay, because see that here previous slide, the Li expression, this is a ith element expression, okay, n into 2 into 10 power minus 7 log of terms. So this is given finally for the total, I mean for the conductor A, final conductor A inductance. So which is obtained from addition of the all inductances. So we remembered Li here and Li also there. Expression is n into 2 into 10 power minus 7 log of, okay. So remember for ith conductor, I am talking about the ith conductor, inductance of the ith conductor, ith conductor. So D, so ith conductor, so D I1, right? So this is given by D1I, D2I, and so on, DII, DNI, right? Whole power 1 by N. And the numerator we have 1 dash I, 2 dash I, and so on, M, I whole power 1 by M. So now this is Li expression. So come to the La here. Addition of all L1 plus L2 and so on Li and so on Ln by divided by this whole n divided by n square, right? So what you will get by n square means this n square. So n gets cancelled. We have 1 by n is there. So this 1 by n becomes, okay, it will come here as well as here. So finally the inductance expression, total inductance expression, if you see here, La is equal to 2 into 10 power minus 7 log of, okay, the terms logarithmic of all the terms whole power 1 by mn in the numerator, 1 by n square in the denominator. Now if you see the terms here, 1, okay, first one is D with respect to the first element, right? So 1, 1, okay, 1, 2, and so on like that, okay. Then 1j and so on, 1n up to n. Then with respect to the ith element, di1, okay, this is i1, this is i1, i2, okay. So here also this is this is I1 dash, I2 dash, right? IM. So here D1, D11, okay, and so on, D1J and D1N. Next with respect to ith element, DI1, DII, DIN. Next with respect to nth element, N1, DN1, DNI, and so on, DNN. Whole power 1 by square. In numerator, we have the terms like this, right? So D, first element is 1 dash, right? So 1 dash, so 1 dash here. So first element with respect to first element here, this is given by 1 dash. So 1 dash 1, okay, then and so on up to m, right? So then Similarly, next element, okay. So in conductor B, we have the elements 1 dash 2 dash like that. So the total elements finally, okay, D1 dash, N1 dash, okay, and because total here M number of conductors. Okay, now here finally what they are telling is the numerator in this expression, the numerator of the logarithm is called mutual geometric mean distance. In shortcut, mutual GMD. The numerator here, okay, the above expression, it is called mutual geometric mean distance, mutual GMD. Okay, so with mutual GMD means between the conductors. So here what are the conductors we have? Conductor A and conductor B. Okay, and it is denoted with DM. Okay, D M, D suffix M. Now, what is this? Okay, what is this DM? It is defined as like this here. Mnth root, right? We have seen here what is the root? 1 by Mn, right? So that's why it is defined as like this. Mnth root of Mn terms, okay? Mnth root of Mn terms, okay? Finally, because we have Mn terms, which are the product of all possible mutual distances from nth elements of conductor A to m filaments of conductor B. Okay, so that is about the numerator. Numerator is given mutual, that is a it is a between given. So this is given. So it is given. Um, it is given. It is called mutual GMD because it is given between the conductors A and B. Okay, M and terms both are there. So that means it is between conductor A and conductor B, and it is abbreviated as DM, and it is defined as like this: mnth root of Mn terms, right? So that means product of product of all mutual distances from n filaments of conductor A to m filaments of conductor B. Okay, mutual distances between the conductor A filaments and conductor B. So that's why it is named as mutual geometric mean distance. Next, they say about the denominator. Similarly, the denominator of the logarithm is defined as self geometric mean distance, self GMD, self GMD of conductor A. Okay, and it is defined and it is abbreviated as DS, D suffix S. Okay, see that it is named as self GMD of conductor A. That means only conductor A. Okay, that's why the name also self GMD. Okay, it is denoted with DS, and see how it is defined. Okay, they're telling it is also sometimes called GMR, geometric mean radius. Anyway, how it is defined? N square root of, because you can see here, right? We have the n square. Nth square, n square root of the n square product terms. Each set consisting of r dash for that element and n minus 1 distances from that element to other in the same conductor. Okay, so it is a self with respect to conductor A only. So how it is defined? Nth square root of the n square product terms. Okay, that means what? It's consisting of r dash means it's with respect to its own radius 0.7788 into r, and also what are the other things? N minus 1 distances from other filaments to that particular filament. So that is how GMR, okay, and mutual GMD are explained. So finally, which is given expression 2 into 10 power minus 7 log of the upper one is what? Mutual GMD, right? Which is denoted with DM, and the denominator is self GMD, right? Which is denoted with DS. Okay, with respect to conductor A, it is writing, so it is, that's why it is mentioned as DSA. Okay, 2 into 10 power minus 7 log base E dm by ds. Okay, with respect to conductor A. Similarly, conductor B also the same. Okay, 2 into 10 power minus 7 log of dm by dsb. Finally, the total inductance of the single phase transmission line, okay, which consisting of the standard conductors La plus Lb. So which is given by 4 into 10 power minus 7 log of dm by ds. Okay, so this is the final expression for the inductance of a single phase transmission line, which consisting of the stranded conductors or composite conductors, where dm is mutual GMD, ds is self GMD. Okay, self GMD. If you remember, for a single, if the transmission line having the single conductors, what is the inductance? Log of d by r dash, right? That is a transmission line with single conductors, where d is a distance between the two conductors, capital D. R dash is a R dash is a okay, R dash is a 0.778 into 0.7788 into R radius. So that is previously the expression. Now for a composite conductor, this is a standard conductor, this is the expression which have the mutual GMD and self GMD. Okay, next we have a small problem based on this composite conductors. Okay, in a single phase line, conductors A and A dash in parallel from one circuit, while conductors B and B dash in parallel form the written path. Calculate the total inductance of the line per kilometer, assuming that current is equally shared by two parallel conductors. Conductor diameter is 2 centimeter. So the diagram given where they're telling that one path is having A dash conductors, okay, go conductor like this, and the other conductor B, it has two conductors B dash, which is a written path. So that and they have given in the diagram distance between the conductors like this, okay, and distance between the conductor A and B is shown like this 100 centimeters, and again this distance is 20 centimeters, B and B dash between distance. Okay, now what is how to calculate? What they asked, calculate total inductance. So we know that just now we have seen total inductance for the line is 4 into when there are stranded conductors like this. We have seen, just now we know, right? Conductor phase in having the two conductors A dash means it is a composite conductor. So 4 into 10 power minus 7 by log dm by ds log base. So minus 7 is written as here, it is minus 4 because it is written units henries per kilometer. Okay, because they have asked the inductance per kilometer. That's why the in the expression 4 into 10 power minus 4 henries per kilometer. Now in this we have to calculate the dm and ds. So then we substitute. Now first, what is dm? Mutual GMD. We know that how to calculate that. We have to consider the distances between the two conductors, right? Mutual distance between the two conductor A and conductor B. So where dm is given by fourth root of, okay, dab, dab dash, da dash b, da dash b dash. That is how Okay. For a single phase stranded conductor, the mutual GMD is calculated.
Like, share and subscribe. Hit the bell icon for more updates.